Today we'll be dealing with the ninth video of the module 4 in Power Electronics, BE 7th semester Electronics and Communication Engineering, Belgavi. In this module we'll be dealing with the DC to DC converter. We'll continue with it. We have been looking into different types of choppers and we are going to refer to the textbook Mohammad Rashid, Power Electronic Circuit Devices and Applications. So in this particular video, we'll be looking into the switching mode regulator, and we have already dealt with buck regulator and boost regulator in the previous classes out of the 4 types of regulators. In this particular video, we'll be looking into the buck boost regulators, and the cuck regulator and chopper circuit design will be looking into the forthcoming videos. Coming to the classification of converters, we have seen the buck converter, which is nothing but the step-down converter itself. Boost converter, we have seen that it is basically has output which is greater than the input. Now, when we look at the buck boost converter, a buck boost converter will be shown, and the output voltage can be either higher or lower than the input voltage. So that's it has both buck and boost incorporated in it. And cuck regulator, we know it is basically actually pronounced as chuk, and it's a type of DC to DC converter that has an output voltage magnitude that is either greater than or less than the input voltage magnitude. And it is basically a boost converter followed by a buck converter with a capacitor to couple the energy. So these are the 4 types of circuits that we'll be looking at, and we have already seen the buck converter and the boost converter. This is basically the circuit for buck boost converter, which is a combination of a buck and boost converter. We have this switch element in series with the supply as in a buck regulator, and we'll be introducing the inductor and the diode which will carry the load during the mode 2 of the operation. So for basically the converters, buck boost regulators, it provides an output voltage that is less than or greater than the input voltage, hence the name buck boost. Okay, so it has both output less and greater than the input voltage. The output voltage polarity is opposite to that of the input. This is to be noted. The output voltage polarity will be opposite to that of the input voltage. This regulator is also known as the inverting regulator because of that. Now this is your buck boost regulator. The circuit is as shown above, and the circuit arrangement of the buck boost is basically having this switching element. It could be MOSFET, transistor, IGBT, anything in series with this supply voltage. We have an inductor connected in parallel with the load. We have a DM or diode connected in this opposite, which is taking the load current in this direction, and we have the capacitor also connected across the load. Thus, transistor Q1 will act as a controlled switch, and the diode DM is an uncontrolled switch. So these two are the switches, and they operate as two SPDT. So I can convert this circuit equivalent to a an equivalent circuit, which I will be showing soon. And we can replace it with maybe an 2 SPST current bidirectional switches. Okay, so how are we looking at? So this is how the circuit buck boost regulator can be shown with the switch representation. This switch and this switch will be having, like, the switching position could be in 1 or in 2 depending upon the mode of operation. So the circuit here is represented with these switches, and we can divide it into 2 modes of operation. During mode 1, the transistor Q1 will be turned on and diode DM will be reverse biased, and the switch here is said to be in this position 1. Okay, and during this mode the transistor Q1 during mode 2, when the switch is in this position, the transistor Q1 will be switched off and the current which is flowing through the inductor will flow through L, C and the DM. So in this fashion. So these are the two modes of operation. When the switch is in this position, we have this mode 1 where only switch Q1 is on and the current is flowing through the inductor. And we also have the load this side, this circuit, which will be in closed loop, and the current will be flowing basically from the capacitor to the load in this direction, discharging type. And in equivalent mode 2, we have got this switch is off, so this element, this is coming in this position, so we have this inductor, and then we have this switch 2 which is on, this diode, okay, connected, so this acts like a short circuit, and we have the capacitor and the load connected in this fashion. So these are the two modes of operation. Let us see how they work. So in mode 1, the input current will rise and flow through the inductor L, input supply inductor L and transistor Q1 because it is turned on. In mode 2, the transistor is off and the current which will flow through the inductor L would flow through L, C, DM and also the load. So the energy that is stored in inductor L would be transferred to the load and the inductor current would fall until transistor Q1 is switched on again in the next circuit. So we'll see the rise in current in mode 1 and the fall in current in load 2. The equivalent circuits have been shown to you, and the waveforms, let's see, for the steady state voltages and currents of the buck boost regulator are shown for continuous load current. So let us look at the waveforms here. So this is the on time, chopper is on, and this is the off time when the chopper is off. Okay, and here we are seeing the inductor current here during the mode 1 T1. When the chopper is on, the supply voltage gets connected to the inductor in this fashion, and the current is flowing from top to bottom from the inductor. The direction of current arrow is like this, and hence the current is also shown as rising and positive from I1 to I2. So the current will flow in this direction. The supply voltage will be plus minus Vs, that is the input supply. Then diode is not there into picture because diode is off in T1, that is in mode 1, and hence what we can show is there is no diode current, that is I1, there is no diode current which is flowing during T1. We have seen the capacitor is connected to the load, right, and the capacitor current, the load is flowing in this particular direction, and we are assuming that the load current actually flows and the current is said to be constant, which is equal to I. So the load current is flowing in this direction and the capacitor current is shown like this, but the load current will freewheel like this. Hence it is opposite to the direction of IC shown, and hence it will be in negative I. So this is the load current carried by the capacitor, but it is from top to bottom. Arrow is shown in this direction, hence I show the capacitor current same as the load current but in the reverse direction. Then the capacitor voltage during this time will be of the falling type, okay, through the load. Now, when in mode 2 the switch turns off and we'll have the diode D1 conducting. The minute diode D1 conducts, the current that is flowing through the inductor, you can see it will continue to flow in the same direction. So the current will remain positive in the inductor, but it is of the falling type and it is supplying the current to the capacitor and to the load. So the capacitor current, earlier it was coming like this, so now it is going in the opposite direction. So the capacitor current will reverse, right? The current through the inductor will continue to be positive in this direction, and this current which is through the flowing through the capacitor and DM will be the same current that is flowing, and we will have the current flowing through the inductor in this fashion. So the capacitor through the DM also it will be in the same direction, right? And the capacitor also will carry that current. and the current through the load, we are assuming it to be same, always DC and fixed. Now when the current through the inductor is flowing, and in the mode 1 it was plus minus, when the switch opens, the property of the inductor is to reverse its polarity, plus minus. Okay, and hence earlier we were assuming the load voltage to be 0 when there is no connection, but during this time the load voltage will be negative. So assuming that the inductor current during the mode 1 is rising from I1 to I2, and the inductor comes across the supply Vs, the voltage across the inductor can be written as Vs is equal to L into di by dt. Di by dt means di is delta I, which is I2 minus I1 by T1, and hence I can write it as L into delta I by T1, where delta I is nothing but the change in the current I2 minus I1. Or during T1, bring this on the left hand side, I will get delta I, L into delta I by Vs. During mode 2, that is during T2, the inductor current is falling from I2 to I1. And in this time, the voltage across the inductor will be same across the supply, and that is nothing but Va is equal to L minus L into di by dt. So minus L because we are taking the slope which is of decreasing type. So it will be basically minus of I2 minus I1. So it will be delta I by T2, and D2 becomes equal to minus delta IL by Va. And hence delta I is I2 minus I1 is the peak ripple current of the inductor. So for the output load voltage equation to calculate, we know that T1 is I delta I by L by Vs and T2 is minus delta IL by Va. So I get delta I equal to Vs into T1 upon L is equal to minus Va T2 by L. Substituting T1 as Kt and T2 as 1 minus Kt, the average value of the output voltage will be Va is equal to minus Vs into K upon 1 minus K. Now coming to the average output load current, what we can do is, since we know that T1 is equal to K into T, T can be written as 1 by F. Therefore, K becomes equal to T1 into F. So if I substitute this in this equation, Va is equal to minus Vs into K upon 1 minus K, that is going to yield T1 is equal to Va upon Va minus Vs into F. Okay, so we get one T1 another equation for T1. Assuming lossless circuit, we know that the input power, that is Vs into Is, is equal to the output power, and in this case output power is Va into I, but it is with negative sign. So this becomes equal to Vs into, we know that output voltage is Vs into K upon 1 minus K, right? Vs into K upon 1 minus K, substitute that, and the average input current Is is related to the average output voltage. Because of this, the Vs and Vs cancels, and we get Is is equal to Ia into 1 minus this minus and this minus cancels. So we get Ia into K upon 1 minus K. Okay, so this is the relation between the input current, supply current, and the output load current. Now let us look at the peak to peak inductor ripple current, that is delta I. We know the switching period T can be found from T is equal to 1 by F equal to T1 plus T2, which is equal to, we know that T1 is delta I by L upon Vs, T2 is equal to minus delta I L by Va. Substituting for T1 and T2 here, I'll be getting an expression delta IL into Va minus Vs upon Vs into Va. And this is going to give me the peak to peak ripple current. So I'll take delta I on the left hand side. So I get Vs into Va divided by this F into L, Va minus Vs, which that will come on the denominator. So this becomes equal to delta I is equal to Vs upon Fl, and VA upon VA minus VS can simply be represented by K using this particular formula. So reassembling it, K becomes equal to VA upon VA minus VS. So delta I becomes equal to VS into K upon FL. The average inductor current is given by, we know the average current through the inductor IL is equal to the IS supply current during mode 1 and the load current IA during mode 2, and that becomes equal to K into IA upon 1 minus K plus IA. So IA becomes equal, that is equal to IA upon 1 minus K. So this is basically the current through the inductor, the ripple current and the average inductor current. Now let us look at the peak to peak capacitor ripple voltage. When the transistor Q1 is on, the filter capacitor is the one which supplies the load current for T equal to T1, right? And the average discharge current of the capacitor IC becomes equal to minus IA, and the peak to peak ripple current of the ripple voltage of the capacitor can be shown as delta Vc is equal to 1 upon C from 0 to T1 minus IC dt, which is equal to 1 upon C 0 to T1 IA into dt, because IC is equal to minus IA. Substitution, I will get IA into T1 upon C. So substituting for T1, we know T1 is equal to K into T. K is equal to VA upon VA minus VS, we have seen in the last slide, and T can be written as 1 by F. So I will get an expression for T1 equal to VA upon VA minus VS into F. So delta V becomes equal to IA into T1, that is VA upon VA minus VS into F into C, or delta VC can be written as IA into K upon FC. So now let us look at what is the condition for continuous inductor current and capacitor voltage. So if I want a continuous current and not discontinuous current, there is a particular or critical value for the inductor and capacitor value. So if if IL is the average inductor current, okay, so if IL is the average inductor current that is flowing at the critical condition for continuous current, conduction of the inductor current, then I can say that delta IL is nothing but 2 times IL, right? Because IL becomes equal to delta I upon 2, where delta IL is I2 minus I1. So delta I becomes equal to 2 times IL. I have explained this earlier also. And also we know that Vs or delta I is equal to Vs into K upon FL. So substituting delta I as 2 kVs upon FL, this becomes equal to 2 times IL. IL is nothing but the load current, that is 2 times IA. So this becomes equals to 2 into K into Vs upon 1 minus K into R. How we get this is IA can be represented as VA upon R, and VA we know is equal to VSK upon 1 minus K. So this expression becomes equal to 2 into VA upon R. So VA I have replaced it as K into Vs upon 1 minus K. This gives me the critical value of inductor LC, which is becoming equal to, so I take L on the left hand side. Okay, so I get L becomes equal to 1 minus K into R. Okay, KVS gets cancelled upon 2 into F. So I get this expression for the critical value of the inductor. Now similarly, what should be the critical capacitor value? For that, I will get it from the ripple voltage. The ripple voltage across the capacitor at the critical value, we know it goes up and down. A critical condition for continuous conduction current. So if I am considering the average as minus VA, then delta VC becomes equal to minus 2 into VA, because delta VC by 2 becomes equal to minus VA. So delta VC becomes equal to, we know that VA can be this becomes equal to IA into K upon FC. So I get minus IA K upon FC equal to minus 2 times VA. that is equal to minus 2 into VA can be represented as IA into R. This gives me the critical value of the capacitor CCSC equal to K upon 2F into R. So, in the buck boost, a buck boost regulator, it provides an output voltage polarity reversal without a transformer. So, we are getting an output which is reverse voltage of the input. It has high efficiency, and under a fault condition of the transistor, if the transistor short circuits or faults, then the current increases. But this di by dt of the fault current is limited by the inductor L. But we have got the inductor L that will limit the di by dt, and this will be equal to Vs upon L. However, the input current is discontinuous. We have seen that no current will flow when the transistor opens up or in mode 2, and hence the supply voltage will become discontinuous and a high peak current will flow through the transistor Q1. Now let us look at an example problem of finding the currents and voltage in the buck boost regulator. So the buck boost regulator, as shown in the figure, we'll see it in the next slide, has an average input of Vs is 12 volts, duty cycle K equal to 0.25, switching frequency is 25 kilohertz, and the inductance L is 0.150 microhenry, capacitance value is 220 microfarad. The load current IA is also given as 1.25 amperes. You are supposed to determine the average output voltage VA, the peak to peak output ripple voltage, that is VC, the peak to peak ripple current of inductor, that is I, delta I, and the peak current of the transistor IP, and the critical values of L and C. So this is a circuit diagram of a buck boost and we have been given the parameters such as Vs has been given as 12 volts, duty cycle as 0.25, the load current has been given as 1.25 amperes, frequency as 25 kilohertz, inductance value has been given as 150 microhenry, and the capacitance value is given as 220 microfarads. In the first part, you are supposed to find the output voltage. So we know that output voltage is minus k Vs upon 1 minus k. So I get this as minus 12 into 0.25 divided by 1 minus 0.25. So that comes out to be minus 4 volts. So we have got an input supply of 12 volts and output I am getting a step down value. So it's a buck kind of a circuit working as that, and it gives a negative voltage, that is minus 4 volts. The peak to peak output ripple voltage, we know delta VC is IAK upon FC. So I get an expression for delta VC as equal to IA is 1.25, K is 0.25, F is 25 kilohertz, capacitance value is 220 microfarads. So solving, I'll be getting delta VC as 56.8 millivolts. Similarly, the peak to peak inductor ripple current, we know that the load current is given as IA upon 1 minus K, and let us find the ripple current, which is equal to, as per the formula, 12 into 0.25 upon 25 K into 150 into 10 to the power of minus 6, which is equal to 0.8 amperes. So, coming to the summary of this particular video, we have been looking into the switching mode regulator and buck boost regulator to be specific. We have seen the different derivations for the output voltage. We have seen the ripple current derivation, the ripple voltage across the capacitor derivation. We have also seen what is the required critical values of the inductor and capacitor if the load current has to be continuous current. Now with this all was followed by an example problem that we have solved using the known formulas. So with this I'll be ending this particular video, and I hope you have understood. I thank you, and if you have any questions, do get back to me. Thank you so much.